Calculating the probability of a single isolated event is straightforward, but predicting the aggregate behavior of a massive group requires a different mathematical mechanism. That mechanism is the central limit theorem. It is the mathematical bridge that allows statisticians to extract predictable patterns from chaotic individual data. The theorem establishes a strict mathematical rule. If you extract multiple samples from a population, and each sample size, represented by the variable n, is strictly greater than 30, the distribution of those sample means will form a predictable normal bell curve. This normal distribution of sample means materializes regardless of the underlying shape of the original population. The original data can be heavily skewed or entirely random. To apply standard normal distribution methods to a dataset, you must verify one of two conditions. Either the original population is already known to be normally distributed, or your sample size, n, is greater than 30. If the original population is not normal, and you are constrained to a sample size of 30 or fewer, the theorem fails. The sample means will not approximate a normal curve, and these methods cannot be applied. By guaranteeing a normal distribution for large samples, the theorem allows researchers to execute precise probability calculations on real-world aggregate data, completely bypassing the messiness of the underlying individual variables. Moving from a single individual to an average group requires adjusting how we measure mathematical spread. The first parameter remains stable. The mean of all possible sample means, denoted as mu sub x bar, is perfectly equal to the original population mean, denoted as mu. The spread, however, tightens. We measure this new spread using the standard error of the mean, or SEM. SEM quantifies the standard deviation of sample means, dictating how far group averages drift from the center. To find the standard error, take the population's standard deviation, sigma, and divide it by the square root of the sample size, n. Because the sample size sits in the denominator, the math forces an inverse relationship. As sample sizes grow, the standard error shrinks. The resulting group averages cluster tightly around the true mean, making wild statistical deviations exceedingly rare. We can observe this mechanical difference in an engineering context. In an effort to increase cabin capacity on 737 jets, Boeing engineers considered reducing the standard seat width from 16.6 inches down to 16.0 inches. To evaluate this, they required baseline population data. Ergonomic studies show that adult male hip widths are normally distributed with a mean of 14.3 inches and a standard deviation of 0.9 inches. The first operational question is straightforward. What is the exact probability that a single, randomly selected adult male passenger will have a hip width exceeding the proposed 16.0-inch seat? We find the answer using the standard z-score calculation for an individual value, the target value minus the mean divided by the standard deviation. This chart plots the normal distribution of male hip widths. Executing the calculation, 16.0 minus 14.3 divided by 0.9 yields a z-score of 1.89. Checking a standard probability table for this score gives a cumulative area of 0.9706 to the left of our target. To find the probability of exceeding the seat width, we subtract that left side area from 1. The result is 0.0294, or roughly 3%. A 3% probability dictates that 3 out of every 100 male passengers will not physically fit in the proposed seat. In commercial aviation, that failure rate guarantees multiple accommodation issues on every single flight. Now, consider the alternative perspective. Instead of analyzing a single passenger, we evaluate an entire main cabin filled with 126 randomly selected male passengers. The question changes. What is the probability that the mean hip width of all 126 men on that flight is strictly greater than 16.0 inches? Because the sample size of 126 is well above the threshold of 30, the central limit theorem mechanics govern the math. We calculate the new standard error by taking the original standard deviation of 0.9 and dividing it by the square root of our sample size, 126. The spread drops drastically. The standard error for the group is just 0.1. This chart displays the sampling distribution of mean hip widths using the revised z-score formula. Running the calculation, 16.0 minus 14.3 divided by 0.1 yields an immense z-score of 17.00. This value falls so far into the right tail, it drops completely off standard probability tables. Mathematically, the probability of an entire cabin averaging over 16.0 inches is 0.0001. It is virtually zero. This aggregate probability, however, is useless to the engineers. Airline seats hold individuals, not averages. The microscopic group probability does not negate the 3% individual failure rate, rendering the 16.0-inch width reduction entirely unfeasible. The exact same statistical mechanics used to evaluate strict engineering designs provide the foundation for testing deeply established scientific assumptions. This process relies on the rare event rule for inferential statistics. The rule dictates that if an observed event has a remarkably small probability of occurring under a specific assumption, we must logically conclude that the assumption itself is incorrect. Consider a universally accepted medical baseline, the historical, long-standing scientific belief that the average human body temperature is exactly 98.6 degrees Fahrenheit. Under this assumption, our population mean is 98.6, with a known standard deviation of 0.62 degrees. Researchers at the University of Maryland tested this assumption by pulling a random sample of 106 subjects. They recorded a mean body temperature of 98.2 degrees. With a sample size of 106, the central limit theorem applies. Dividing the 0.62 standard deviation by the square root of 106 provides a standard error of approximately 0.0602. This chart plots the expected distribution of sample means. The z-score calculation determines how far the 98.2-degree finding deviates from the center, returning an extreme z-score of -6.64. The far left tail reveals a microscopic probability of 0.0001. This creates a strict dichotomy. Either the assumed average of 98.6 is perfectly correct, and the researchers happen to document a 1 in 10,000 biological anomaly, or the underlying mathematical assumption is demonstrably false. Applying the rare event rule, the probability is too low to accept as random chance. The mathematical evidence proves the historical belief is wrong. The true average human body temperature is actually closer to 98.2 degrees. When deploying the central limit theorem on real-world populations, there is one final critical mechanical caveat regarding the standard error. It applies specifically when sampling without replacement from a closed, finite population designated by capital N. If your sample size, n, accounts for more than 5% of that total population, the standard error formula must be multiplied by a specific adjustment, called the finite population correction factor. This necessary mathematical adjustment prevents catastrophic statistical distortion. It ensures the mathematical spread remains perfectly accurate, even when your sample consumes a massive, significant percentage of the entire group being studied.